In this section, we define an operation on vectors called the dot product. This concept is especially helpful in calculus and applications of vectors in physics and engineering. So let's talk about the definition of a dot product. It's very easy. If you have vector u, and we'll call that a1, b1, and vector v, which is a2, b2, the dot product, which looks like a multiplication problem, all you have to do is multiply the first component, or the horizontal component of each vector, and then add to that the product of the vertical components. Note that the answer you get is not a vector, it's a scalar. That means it's just a number as opposed to something with an I and a J in it. So let's do an example where we're going to find the dot product. Again, very easy stuff here. So if u is vector 3, negative 2, and v is vector 4, 5, then the dot product u dot v can be found by multiplying 3 times 4 and adding to that negative 2 times 5. So 12 minus 10 is 2. Now, remember there are two ways to represent vectors. There's this way between the little things that look like inequality symbols, and the other way is using I and J. So if instead I give you a problem that says vector u is 2i plus j, and vector v is 5i minus 6j, then when I find the dot product, I multiply the i's, so 2 times 5, and I add to that the j's, 1 times negative 6. So I get 10 plus negative 6, which is 4. So again, the dot product is very easy. The dot product follows the properties of real numbers that you know go with addition and multiplication. So the dot product is commutative. That means that it doesn't matter what order you multiply the vectors in, you'll get the same scalar answer. The other thing that you could do is you could do a little distribution. If you multiply a scalar times a vector and then do the dot product, it doesn't matter. I could have done this instead. Oops. I could have multiplied that scalar times the other vector first before I perform the dot product. So it follows the distribution property. It also follows the associative property. So if I want to add two vectors and then do the dot product with a third vector, it's the same as if I were, I guess that's, what I'm writing is and what I'm saying are not the same thing. This is my distributive property, sorry. If you square the magnitude of a vector, it is the same as doing the dot product of a vector with itself. Let's say I wanted to know the angle of the between two vectors. Well, there's something called the dot product theorem that says that when you do the dot product, the scalar quantity that you get is really the same as the magnitude of those two vectors being multiplied times the cosine of the angle between them. Because that is true, if I wanted to find the angle between two vectors, I could divide both sides of this equation by the product of the magnitudes, and I would have an equation for finding the angle. And this is really the important formula, the formula for finding the angle between two vectors. is the inverse, or sorry, it's the cosine of theta is equal to the dot product of u and v divided by the product of the magnitudes of the two vectors. I'm going to find the angle between vectors u and v if u is 2, 5 and v is 4, negative 3. So the formula says that the cosine of theta is equal to the dot product of u and v. So 2 times 4 plus 5 times negative 3 divided by the scalar quantity of each vector. Well, the scalar quantity of vector u is the square root of 2 squared plus 5 squared. And the scalar quantity of vector v is the square root of 4 squared plus negative 3 squared. So now I'm going to do some simplifying. On the numerator, I get 8 plus negative 15, which is negative 7. In the denominator, I get the square root of 4 plus 25 is the square root of 29, times the square root of 16 plus 9 is 25. And I'm going to end up with the square root of 7 over the square root of 729. Alright, so now in my calculator, I'm going to do the inverse cosine of negative 7 divided by the square root of 729. And that's going to give me approximately 105.1 degrees. So the number of degrees between those two vectors would be 105.1 degrees. Two vectors are said to be perpendicular or orthogonal if the dot product of the two vectors is 0. Now remember, perpendicular lines are ones who have a 90-degree angle between them. So if two vectors have a 90-degree angle between them, the dot product has to be 0 because the cosine of 90 degrees is equal to 0. So let's do an example where we check for orthogonality or perpendicularity. Let's determine if vector u at 3, 5 and vector v, whose components are 2, negative 8, are orthogonal or not. Well, 3 times 2 plus 5 times negative 8 is 6 plus negative 40, which is negative 36. They are not perpendicular. But let's try this again. Let's say we have vector u whose components are 2, 1, and vector v's components are negative 1, 2. So 2 times negative 1 plus 1 times negative 2. Negative 2 plus... Oh, I screwed that up, didn't I? I did, because, let's see, this should not be a negative 2, should it? Alright, let's try that again. 2 times negative 1 plus 1 times 2. This is going to be negative 2 plus 2, which is 0, which means that those two particular vectors are perpendicular. In physics and engineering, sometimes it's helpful to express a vector as the sum of two vectors lying in perpendicular directions. Because of that, we come to a concept called the component of vector u along vector v. The component of vector u along vector v, I guess here's my perpendicularity, is a scalar quantity found by doing the magnitude of vector u times the cosine of theta. If the angle between the two vectors is acute, the scalar quantity u lies actually on vector v. If the angle between the vectors is obtuse, the component of u along v is going to lie in the same line as v, but in the opposite direction. Now, the reason we care about these perpendicular direction vectors is because if you think about a car lying on a hill, This would be a car not on a hill, and the only force acting on it is the weight of the object into the ground. But what if I make this at a slight angle? Now there are two forces acting on this. There's a force acting on the car this way. It wants to push it down the hill. There's the force of the weight of the object going into the hill. And then we have this third vector, we're going to call it W, which is the sum of U and V. And that's often the vector we want to deal with. That's the weight of the car directly to the center of the earth, whereas U is the force that tends to roll the car down the hill, and V is the force experienced by the surface of the hill. The bigger the hill, the more the force going down the hill. This becomes bigger. The force of the object on the surface of the object becomes smaller. But it doesn't really change the weight pulling down towards the center of the earth. But we still want you to know that the weight pulling towards the center of the earth is the sum of the force wanting to roll it down the hill plus the force pushing into the surface of the hill. So let's do an example of this component of U along V. And by the way, it's not always U along V. A car weighing 3,000 pounds is parked on a driveway that is inclined 15 degrees to the horizontal. Find the magnitude of the force required to prevent the car from rolling down the hill. So I drew a picture here. I've got the car on the hill, and we have vector U, which is the force pulling it down the hill. Vector V is the weight of the object into the hill, and W is the gravitational force, the force of the weight of the car towards the center of the earth. So in order to find the magnitude of the force required to prevent the car from rolling down the hill, we want to find, let's use a different color here, we want to find the magnitude of U. And the magnitude of U is going to be the component of W along U. So the component of W along U, the magnitude, is 3,000 pounds. And then the cosine of theta, theta is the angle between U and W. The reason we're using U and W is because we want to find the force keeping the car from rolling down the hill. Now, that angle up there is not 15 degrees. This angle here is going to be the same as the incline of the hill. So this angle here is 15 degrees. And since U and V are perpendicular, that makes the angle between U and W 75 degrees. So I'm going to change that theta to 75 degrees. And I'm going to find out that it's approximately 776. So you need a force of about 776 pounds to keep the car from rolling down the hill. In part B, we want to find the magnitude of the force experienced by the driveway due to the weight of the car. All right, let's go back to this picture. If we want to find the magnitude of the force experienced by the driveway, then we want to find the component of W along V. So the magnitude for V is equal to the component of W along V. So it's still the 3,000 pounds, but this time it's going to be the cosine of the angle between U, or V and W, which we said was 15. So the answer is approximately 2898 pounds. So because it's at an incline, The driveway doesn't feel all 3,000 pounds. It feels less than that. And it actually feels about 2,898 of the pounds for this particular angle. The bigger the incline of the hill, the less weight the driveway would feel. What if I didn't know the angle, and I just knew the two vectors for u and v? In order to find the component of u along v, I could also find it by doing the dot product of u and v and dividing it by the magnitude of v. So let's do an example. Let's say I tell you that vector u is 1, 4, and vector v is negative 2, 1, and I wanted to find the component of u along v. All I would have to do is u dot v, which is going to be 1 times negative 2 plus 4 times 1, and divide that by the magnitude of v. And the magnitude of v is the square root of negative 2 squared plus 1 squared. So the numerator is negative 2 plus 4, and the denominator is the square root of 5. So 2 over the square root of 5 would be the component of u along v. And if you want to turn that into a decimal, that's cool. The answer would be about 0.89. Let's say instead of a scalar quantity, I wanted to know the vector of the component lying along v. This is instead called the projection of u along v. The component of u along v was a scalar quantity, so it was a numerical value. The projection of u along v is going to be a vector. It's found by taking the dot product of u and v, dividing it by the square of the magnitude, and then multiplying it by vector v, in which case the final answer will be a vector. The way we write this is projection sub vector v, then the big vector u. If the vector u is resolved or broken into vectors u1 and u2, where u1 is parallel to vector v and u2 is perpendicular or orthogonal to vector v, then we can break it up by writing vector u1 as being the projection of u along v. Vector u2 would be u minus the projection. All right, let's do a simplistic example where we're going to find the projection of u along v. Vector u is negative 2, 9. Vector v is negative 1, 2. We said in order to find the projection of u along v, we're going to start by taking the dot product. So the projection of u along v is going to be negative 2 times negative 1 plus 9 times 2. We're going to divide that by the square of the magnitude of v. Now, remember when you take the magnitude of v, you're taking square root, so a square of a square root cancels, so it's really just negative 1 squared plus 2 squared. And then we're going to take that answer and we're going to multiply it by vector v. So I'm going to get 2 plus 18 over, let's see, 1 plus 2 is, or 1 plus 4 is 5. Uh, 18, 19, I get 20 over 5, which is 4, and then the properties of vectors say that I just distribute that 4, I get negative 4, 8. So the projection of u along v is the vector negative 4, 8. What if I wanted to resolve these vectors into the components u1 and u2? What is the vector parallel to v, and what is the vector that's perpendicular to v? Well, u1 is easy because u1 is just the projection of u along v, so I already know that answer. It's negative 4, 8. I found it in the previous problem. Vector u2, however, is going to be vector v, which is negative 1, 2, minus the projection. And again, we just use the properties of real numbers to do this. So negative 1 minus negative 4 is going to be, well, let's try that again, because it's not v minus the projection, it's u minus the projection. So it's negative 2, 9 minus the projection. Sorry about that. All right, negative 2 minus negative 4 is going to be 2. And 9 minus 8 is going to be 1. So u2, the vector that's perpendicular to v, is going to be 2, 1.